Hi, welcome to the Signal Path. I have another repair slash teardown video for you guys. There is an eBay seller that's been selling a whole lot of Fluke handheld meters that are all broken, and it's a surplus seller on eBay. And I happened to follow around a couple of his units, and I managed to pick one up. This is a Fluke 196B, which is a handheld oscilloscope, very popular. And a lot of people own this unit and are very happy with it. This is a 196B model. There is a 196C model that has a color display. There aren't really that many broken ones on eBay. I wasn't really able to find one. But this one was advertised as non-functional, advertised that does not power on. So I was able to pick it up for just about $200. There was a lot of people bidding on it, which is, it's a lot of money. If I'm not able to fix it, I'm left with a $200 paperweight essentially. And it actually doesn't have a back cover. The back cover is missing. Now I don't know why the back cover is missing. Maybe they removed it and they were selling it and using it for something else, or maybe this is like a bin of something that was damaged. I'm not sure, but all the ones that this seller was selling didn't have the back cover. And I happened to check, the back cover is really expensive. If you want to buy it from Fluke, it's about $100. So I didn't buy that because I wanted to make sure that I can at least fix it. I didn't want to invest another $100. When these things are functional and they have the accessories with them, they sometimes sell upwards of maybe $1,500, so they're not cheap. And this particular model, the 196 series, has a 100 megahertz 2-channel and at 1 gigasample per second, and it should last about 4 hours on battery. So it's pretty good. Although I have a few oscilloscopes in my lab, I've always wanted something handheld that I can maybe take outside when I'm working on something else, or if I want to just do a quick measurement and don't want to bring all the probes out and connect it to the oscilloscope. I keep the lab really clean, so for me to have to dig out all the probes, it's not as straightforward. So this one, if it's sitting on a table, I can move it around. I'll be very happy with it if I can fix it. One thing I did though is that I did buy a battery for it for about $20 from a US seller, so we'll take a look at that. I wanted to make sure that it works with the battery, so I did invest in that without knowing if I can fix it or not. So what I want to do is I want to take a look and see, if it doesn't power on, follow the traces and find out what's wrong with it, and hopefully we can fix it and then start using it in the next videos. So let's take a closer look at this. This is all that I received. No other accessories, no power supply, no cables, nothing. Just this and the top cover, which I'm very happy to receive this because even this thing is quite expensive. So this just sits at the top, and it came in 2 pieces for whatever reason. But it looks like it's in good shape, and it even has a calibration date on it that was calibrated in November of 2011. So it's not that bad. And so the unit itself, it looks like it's in good shape. There is actually a couple of signs of damage on here, which I hope isn't going to cause a problem. Let me zoom in here a little bit. So for example, I can see a minor dent here. There is a small dent here right on top of this ribbon cable, and I'm hoping that this ribbon cable is actually doesn't have a damage on it, because otherwise this looks like it goes to the display. So if that's cut, then even if it powers on, maybe the display won't work properly. And this, both the analog or the RF channels rather, have a shield, an aluminum shield on top, which they should, of course. But this one, if you look, is not sitting in its correct place. It looks like something has crushed on top of this and has caused the aluminum cage to kind of flatten out. So again, I don't know what's going on underneath it, but I hope the components are not damaged. I just received this in the mail, so basically this is off the cuff. Whatever I see, I'm going to tell you. So let's take a quick look. It looks like I can remove this panel. I'm going to use the WeHa screwdrivers that I showed you in one of the earlier videos. I've been very happy with these. If there is one complaint I have about these screwdrivers, is that sometimes the handle isn't thick enough, so you don't get a very good grip. You're gonna have to, if the screw is very tight, it's a little bit hard to open it. But other than that, I haven't been able to damage the tips of these screwdrivers, even on some rough screws. So they're definitely very good. Expensive, but I think they're gonna last for a very long time. So let me get rid of these. So please bear with me to get rid of these things. It looks like there is one more. So I'm not sure what I'm going to do if I'm not able to repair it. but I'm sure some of you guys might have some ideas. There we go. That looks good. Make sure I don't lose these screws. So immediately I can see and recognize some of these components and what the possible function on each of them might be. So this is the battery connector right here, and there is a filter here, which this is a low-pass filter structure, which is an inductor and a capacitor inside it. These two LEDs, I can tell immediately that this is the infrared port of this unit, because it has you can connect it with an infrared connector, so that it can be fully sealed and communicate with the outside. I can see. Let me see. There's of course a couple of capacitors in there. This looks to be like the charging circuitry, which will charge of course the battery. The AC, or rather the adapter plug, is right here, and it looks like it has some cables that run across and end right here. It's a little bit surprising to me, because these cables are running right next to the analog channel. Now I'm sure that they have taken good care of to shield that, but if your power supply is noisy, I wonder if it would couple into this channel right here. Other than that, everything else is just a bunch of ASICs. It looks like it has 3 main ASICs. There's this one that has some numbers on it, which is probably the main boot ASIC. And there is another 2 custom ASICs. Both are Fluke branded, either probably designed by Fluke, or maybe rebranded by Fluke from somebody else. It looks to be some kind of a memory right here, which is in a separate module, so probably upgradable. This I recognize. This is the Flyback converter to power on the backlight, and you can actually see underneath the ribbon cable the backlight connector. So this is not an LED backlight, it still uses a CFL tube. So it looks like I can just unplug that. There it is. There you go, and that reveals the high voltage cables that go to the backlight of the LCD. So this is actually not the LCD connector. I think this might be just a keyboard connector. So that's in a way that's better if this is damaged than this one, because this is a much finer cable. This is the ribbon cable that I think connects to the display. And there is some hair in it. All right, and what I recognize, of course, there's the buzzer, a whole bunch of various passives, a lot of capacitors, some analog devices, A to D converters, I believe these two are. There is a Xilinx Cpld, which is reprogrammable, probably again takes care of some minor function, because it has its own crystal. And again, any of the major DSP is probably done by this guy and this guy. These guys are transformers, probably multiple tap transformers, in order to bring a signal in and out of these channels. So this is because this guy has a built-in meter as well. So the meter goes under this can, and the 2 RF channels are probably identical, and they go up and down there. So you know what, before I take it even further, let me just, for the sake of plugging it in, let me plug it in once and see what happens. So let me put this back, and I'll be right back. So I wanted to power this on and see if you know what happens if it draws any current. Maybe it has a simple problem, and I don't actually have anything really that fits perfectly in the adapter plug, but this guy does kind of fit. And I looked up the data sheet for the power adapter for this, and it is a 17.8 volt power adapter, where the outside of the connector is the positive and the inner one is the negative. So it's, it seems like a little bit backwards. So let me plug that in there. It looks a little bit loose, but it seems to work. So I'm going to try and connect it. So the marked one, I believe, goes here. And there we go. I don't think it's in the frame right now. There it is. So all I did was I connected the unit directly to my Regal DP1116A. So let's turn that on. And what I'm going to do is, let me flip it forward like so. Although I know, let's see what happens anyway. I was gonna use a meter to measure it. So first, Let me go up slowly, so if there is a short or something, or if somehow it's backwards, I'm not going to damage it. So I'm turn it on and go slowly up. 1 volt, 3 volts. No, it's not taking any current yet. Oh no, it's taking 2 milliamps at 5 volts. 8. Still 2 milliamps. Oh, now it's taking 5 milliamps. Well, it's doing something. 15 milliamp. Oh, okay, that's okay. I thought for a second it was taking 1 amp. No, it's taking 79 milliamp at 1.18 watts. It's 15 volts. So let me go to 17.8. There it is, 17.8 volts. It's taking 1.21 watts and 68 milliamps from 17.8 volts. So let me see. It's a power button. Oh, it actually powers on. The screen looks a little bit faded, but it powers on. It was advertised as does not power on. I don't know how they tested this, because it does power on. I don't know if it works, but actually I bought it because it said it does not power on, because usually it's easier to fix something that doesn't power on at all than to fix something that partially works. Because, for example, let's say one channel doesn't work. I cannot fix that because that's most likely the A to D converter, and I cannot replace that. But I bought it because it does not power on. Now it does power on. I don't know if I'm disappointed or if I'm happy about that, because let's say if it has a fault, then it will be much harder to fix. But when it does power on, it's taking about 500 milliamps, 8.8 watts from 17.8 volts. The other possibility is that it powers on AC, and they never tested that, and it doesn't power on from a battery. That could be a problem. It could be maybe the battery part is broken, but the AC part works, or maybe it doesn't charge the battery. So we'll have to test that. But now that it's powered on, I'm eager to find out if it can actually display a signal. So let me get some cables. So what I've done is I've connected 2 BNC cables directly to, let me take this camera out for a second. So there we go. I've connected 2 cables directly to my Regal DG5352 arbitrary waveform generator, and I'm going to put on one channel, let's say, I don't know, 10 megahertz, and on the other channel I am going to put let's say 20 megahertz, and I am going to put both of them, well, they're both on 5 volt peak to peak, so let's put them on 1 volt peak to peak, and put the, oops, and on the other channel put also 1 volt peak to peak. There it is. So we have 20 megahertz, 10 megahertz, 1 volt peak to peak on both channels on a high impedance configuration, so that it is actually, it does not expect the 50 ohm termination, because I don't think the 196B can give you that. So let's see what happens if I connect it to the Fluke. It would be interesting if it actually does the correct thing, because if it does, then I have no idea why they listed this as a broken unit. So I have to be a little bit careful here. So let me turn it off while I do this. There we go, one channel, connect, no problem. The other channel connected, no problem. There we go. Alright, so we power it back on. Alright, so let's take a look at the display here more carefully, if I can get this out of here. There we go. So right now I know that you guys probably see quite a bit of flickering from the camera, but in real life it does flicker a little bit. So maybe the backlight is not doing so well, so maybe there is still something for me to fix, because I was disappointed that there's nothing to fix. Let's see, so let me turn it on. I'm gonna enable the channels. Now you should, oh, it's actually on a 10-to-1 probe, so let me see now, how do I do that? There we go, probe 1-to-1. There we go, that's good. Channel B, probe 1-to-1 also, like so. and I want to turn channel B on. There it is. So it's showing both channels. Nice. So I'm going to enable the output, and there it is. Oh, it's doing something. It's thinking. Oh wow, it actually does a very good job, and it seems to be working perfectly fine. I don't understand. It's 200 millivolts per division. Channel A has 250 and 250. 1 volt peak to peak. Is that right? 1, 2.5. Yeah, that's perfect. That's 1 volt peak to peak. It's exactly what it's supposed to be. Let me turn channel B off, and let me go into channel B and turn it off, and let's examine carefully. This light is probably not very good. There we go. Let me examine and see. So this is now displaying a 10 megahertz 1 volt peak to peak signal. It seems perfectly fine. I don't understand why they're saying it's not functional. So let me try maybe different frequency. Let me try 100 megahertz. There we go, and it will. No, it's perfectly fine again, and it doesn't do a very good job in changing the. I mean, what happens if I press the auto button? Manual, auto. Well, let me try to go 200 megahertz. Oh no, wait a second. 100 megahertz is its maximum. Oh, this is okay. So this is its absolute maximum measurement. So this cannot do any more than that because it's only 100 megahertz unit. So I can do. Let me try instead. Let me go back to 25 megahertz. Let's say. I'm trying to hold this by one hand and operate. So 25 megahertz. Let's see. There it is. Okay. 25 megahertz. Let me make the amplitude much smaller. Let's try 10 times less. 0.1 volt peak to peak. There you go. Still perfect. Wow. Let's try 10 millivolt peak to peak. Millivolt peak to peak. It seems to have a little bit of. No, it's actually correct. This is 10 millivolt peak to peak. So it's doing a very good job, and it actually does a very good job recovering from going from a large signal to a small. So if I go right now from 10 millivolt peak to peak directly to 1 volt peak to peak, it should. There you go. It goes back to it's working very well. I don't understand why they were saying it doesn't work. Let me try channel B. Turn channel B on. Let me turn channel A off. Enable channel B. Yeah, this is channel B. Oh, I see. Oh, okay. It's triggering still on channel A, so it doesn't do a very good job displaying the signal. So let me change the trigger. There you go. Trigger source B. There, and it corrects itself. Very nice. Again, it seems to be working perfectly. But we're still going to tear it down and check to see if it works with the battery. So before I do any more testing, I like to see if it charges the battery. So I'm going to disable the power supply. So the battery, this particular one is made in China. That's probably why it was so cheap. And this is a 3600 milliamp hour, 25.9 watt hour, 7.2 volt nickel metal hydride battery. And it's supposed to last 4 hours in this unit. So it has a 4 connector cable, which obviously two of them is the actual battery. One of them must be the temperature sensor, and the last one, your guess is as good as mine, maybe a detect to see if the battery's in there or some other type of protection. Maybe it has 2 grounds, I'm not sure. But what I can do is I can do a quick measurement on the power supply, on the battery as it is, to see what charge it's actually holding right now. So I'm going to use the Fluke 196 Comrade Fluke 289, which is considered to be one of the very, very good handheld meters. So let me see if I can get a good contact here. Let me see. There it is, 6.5 volts. So it's actually not charged sufficiently for this purpose. But so let me plug it in and see what happens. I hope it doesn't destroy anything. It seems like it'll only go in one way. So there we go. Put this in there. I think it's supposed to sit in there. It sits in nicely, and I believe it will go in this way. if I can plug it in. Come on. You're making my life difficult. There you go. Tolerance on that connector is not very good. I hope I didn't destroy anything. So, I remember that when there was no battery, it was consuming 1.8 watts. So let me see if it consumes more. It does, it's consuming 10 watts and half an amp when it's powered off. So the question is it charging the battery or is it just doing something nasty? So what I'm going to do is I'm going to measure the voltage of the battery and see if it is steadily going up. Oh, it looks good. 7.7 charging voltage. It must be doing its thing. So it still looks good, even with the battery. Let me measure, let me see what the other things are. So the other connectors, the last one, the black one, seems to be nothing. And there is 0.5 volts DC on the white one. I think the white one is probably the temperature sensor to make sure that the battery is not overheating. And the current actually has gone up. Now it's taking 630 milliamps. So I'm hoping that the charger is still charging the battery. Now it says 8 volts. And it's steadily going up. Well, I hope it's good. I actually don't remember on top of my head what the nickel metal hydride battery charging characteristic is and if this is normal or not. But let's let me for a moment turn the charger off, disconnect the charger, and let's see if the unit powers on with the battery as it is. Because then if it does, then I have no idea why they said this unit doesn't power on. Let's see. No, it works. I don't understand. It shows the battery as almost empty, but it is functional. Well, let me see. Let me turn that on again. Yeah, it's fine. I don't get it. Well, I guess it's, in a way, it's good. I see that these two inductors here, which must be the charging inductors from the buck converter, are actually getting warm. So that must be normal. Nothing else seems to be warm. Well, let's tear it down a little bit more. So let me take a couple of more screws and we'll be back. So I removed the metal can that was right here on top of the actual measurement input ports, and I removed this cable and I removed the cable that goes onto the backlight, as well as the LCD cable, which actually I'm still not convinced if that's the LCD cable because there's something else here. I have to take a closer look. But if you look at the construction, you can see because of this this cable here, which is the backlight, high voltage backlight, you can see that they have placed a metal can here which isolates completely the keyboard connector, the LCD connector, and the backlight connector, and there are all these test points, which I'm sure they have a little jig, something that comes on rest on top of these things and can read data or put data into the unit, so they can do it without disassembling it further, because this part was exposed even when the back was on, so it gives it quick and easy access. And here in the front we can immediately see there's a range relay switch here, which I'm sure will click depending on what you're measuring, and there is some good input protection here. You can see that they've cut out the PCB. This is a typical stuff, I'm sure you've seen it many times. There's a spark gap here that will absorb any high voltage surges that may come in here by zapping it to ground, essentially in a controlled fashion. The relay that's there is a rated for 30 volts. It switches at 5, but doesn't say the current. 350 volts, 8 amps. It's an 8 amp relay, so definitely it will switch in for the current measurement when you're measuring current. So then it just comes right off of the unit. There we go. So actually that ribbon cable is the screen's ribbon cable. It's just folded over. This seems to be completely intact, even though it has some marks on it, but there's no damage, which is good, because I'm sure Fluke is charging $1,000 just for this damn cable, as they're charging for the plastic pieces. So this is the front. I'm not going to take this any further apart. You can see it's just a typical LCD screen, nothing fancy, nothing special. It's not an LED backlight, though I wish it were. And the backlight is flickering a little bit. Maybe the Flyback converter, the inverter for the backlight is not, maybe it's not running up to voltage or for some reason, but it's a little bit hard on the eye. Maybe all of them are like that. If you have one of these, tell me if you feel like the screen is flickering. So let's take a look at the main board a little bit more in detail. There we go. So let me see, it might be too much zoomed in. Here we go. So I think these guys seem like they just come off. I'm not sure what's actually holding them down. Okay, so at the back there is a fan, interestingly enough, and this is just a fan connector that comes in, and the fan is completely closed at the back, and I believe this is probably blowing right onto the data converters or some ASIC that is power hungry in order to keep the temperature of the unit down when you're holding it in your hand. So let me take these two stands off, which I believe is what's holding the main board. There we go. Yep, this is definitely holding the main board. There's a washer in there, which we will get. And this is the other one. The board is beautiful, as all of Fluke's designs are top-notch. The soldering is very nice. I don't see any fixes or botches or mistakes that they have corrected with a piece of cable or something, so you have to bear with me. I don't have Dave's fancy fast forward video editing capabilities here. There we go. There goes the two washers. Perfect. So let's put these away. Now before I take it off, I'm going to disconnect the fan. If I can get the tape off, that is. There we go. No problems there. And the fan connector comes right off. So the board should now come out, and it does. Whoa. Alright, so okay, this is the back of that cage that used to be on top of the inputs. So this had a little screw that went through that actually connected to this. So you can assemble. I shouldn't have taken that off at that point, because you assemble this first and then you connect it to the back. So let's take a closer look at the back. Oh, there, just when I was saying that there is no botch job on this, here's one. There it is. A little, what appears to be an inductor in series with a diode, or I'm not sure what the other component is, but whatever it is something that they have obviously missed and have corrected later. So at the back, again, we have a whole bunch of isolation between the inputs and the digital board. All these are optocouplers or some type of isolation between the input and the main board. But what is unusual to me is that there's a lot of flux left on these pins that haven't been cleaned up. I don't know why they haven't bothered to clean this, since they've spent so much time making sure everything else is good. But maybe I'll clean that before I completely close it. But here you can see the cut in the PCB that protects against essentially the dielectric breakdown. This is the PCB is lower than air, so they just use a gap to protect it. And you can see that they have completely shielded the channel, the circuitry that's for the highest speed input channel on the left and the right one, directly from the center. They've cut out all those little notches to make sure there is as little crosstalk between each of the sections, because you can have all three of them active, and if even though you're not using this, you may have it, for example, connected to the main, and you don't want it to pollute the other channels, so you can read good measurements. So again, here's some memory, some ST memory at the back. I believe it, no, maybe it's not ST. I cannot see it very well, but There's some memory there, and there's a whole lot of passives here in the center. In the front, as we examined before, the flyback converter, 2 Fluke ASICs, some memory, probably the original boot up firmware, Cpld Transformers, high-speed transformers, and in fact you can see this is probably where the signal goes in. You can see the 2 traces, 2 differential lines right there. They go this way, and they're length matched to the transformer on the right, because remember that the phase between these 2 channels has to be maintained, because you may be doing a relative measurement between channel A and channel B, so they have to have the same length. So this length and that length are already matched together. There might be some impedance matching passives here, some other more passives probably again to have the impedance matching or to condition the signal. So therefore your ADCs must be in there. So this must be all the DSP in there. Actually, it has some label on it. It says Spider something, but it's now covered by this. It's the name of their chip, I suppose. And again, more transformers. These orange ones or the red ones. And I want to. Well, this is the damage that I was saying. You can see what I don't even know how this could have happened, but I would like to remove that and correct that problem. On the bottom, all you can see is the fan and this plastic rubber, which is a spacer, I believe, in order to make sure nothing touches, because these guys are a little bit elevated, so it probably pushes against the PCB, so you don't short it onto this metallic container. Some isolation here, again, just to protect it from touching the board. And looks good. I'm not going to take the fan off. When it was running, the fan wasn't making any bad noises, so I think the fan is good. It's a 5-volt fan, 150 milliwatt from Sonon, which is made in Taiwan. All good and fancy. So the fan is actually blowing into which way was this? I think it was this way, right here. So it's actually blowing at the back of the PCB right here in this area, which is right behind this guy. So I'm assuming that's sufficient. They probably they couldn't put it on the other side, so they just have some airflow over this entire area to keep it cool. So let's take another step further in disassembling this little guy. There we go. And let's take a closer look here. This is interesting. Oh, I see what's going on here. Okay, so this is the can, the aluminum can that was on top of it. Now this guy is a piece of copper that they have soldered, or yes, they have soldered, or it looks like they have done a point welding. Just a point weld here in order to connect this aluminum to the can. Now, and initially it looks like this is the ground, that it just grounds this this guy just so you have a better contact, but actually it's sitting on top of, oh, something else is in here. Oh, yeah, this is just the stand that was in there. It's sitting on top of this guy. This is thermal putty that's on top of this chip. I believe this must be another analog to digital converter, but this is not the analog to digital converter that does the full sampling, because I believe this is done by here. So this might be maybe a low frequency path analog to digital converter. I'm not sure. There's another relay in here, but whatever it is that is in here, it requires sufficient thermal cooling for them to have created this particular heat sink mechanism. Again, they use copper because copper's heat conductivity is so much better than aluminum. They are, oh, that's my phone. 1 second. Sorry about that. So as I was explaining, they're using copper here because of its good heat conductivity, because they have a very small piece here, so they have to make sure they can get the most out of it. So by tightening this on top of the board, this piece pushes against the thermal putty that's on top of this chip, and therefore will give us a good heat conductivity. I can try and find out what chip that is. I don't want to really remove this because, oh, actually, you know what? It's not, doesn't seem to be very difficult at all. There it is. And this is, what is this? I'll tell you in a second. This seems to be a Phillips part. Part number is N2C8S0. I think it's Philips. Not sure exactly what it is, but I have a feeling it's an ADC, but it's not. I don't believe this is the actual ADC where they do the full conversion. There it is. So there you go. You can see it. So go ahead and decode this. I'm gonna put this back on top of it. So yeah, this thermal putty material is actually, I really like this stuff, and I've used it before. So let me give you a closer look. So it's very soft, but it still maintains its shape, and it comes in big sheets, and you can buy them in different thicknesses. It feels just like putty, but it's not as messy as thermal compound. It may not make as much of a good connection to your device because you can't spread it around like toothpaste basically, because the thermal putty is like toothpaste, thermal compound is like toothpaste, whereas this is more of a putty. But if you need to cut something and put it on top, it works really well, and exactly this is exactly what they have done. So I'm going to put it right back where it is, and it is non-conductive electrically. I don't know what its dielectric constant is, so I have to look it up. But the reason I mention that is because sometimes if this stuff seeps onto traces that are intended to be very high frequency, they have taken the dielectric constant of everything around it into consideration. So if your thermal paste seeps onto the traces, you can change the dielectric constant in their calculation. You can change the dielectric constant. Maybe they have accounted for air to be on top of the board, but then your thermal compound changes that, so the characteristic impedance of the line changes. And if the characteristic impedance of the line changes, then the delay changes, the bandwidth changes, the loss changes, and you're going to run into problems in high frequency design. So this one I don't believe is a high frequency ADC, but again the input is really neat. They have all these cutouts for the various protection and isolation. They have all these capacitors, which I'm sure they're gonna have to look very in detail to see exactly what they're doing, but they're all conditioning the signal. So let me see if I can, for example, trace out where everything is. So the input comes from here, and it goes into these passives right here, these guys, and it crosses over. So this is definitely for protection. Again, because this is an industrial unit, you never know. The technician might connect it to 1,000 volts by accident. I don't know if he can take that, but it's certainly that you don't want this blow up in your hand. So they have done a good job in creating that. So I have to dig out the schematic, see if I can find it online. Then we can take a better look and go over it and see exactly what is happening. So that's the board. I'm going to see if I can, unfortunately I may have run out of alcohol because I wanted to clean these guys, but maybe it's not that big of a deal. And I'm not going to open this one because I'm sure it's a replica of the other one. And I was worried about these cables that come from the connector that run right next to here, but they're outside the cage and they're just right against it. So it's probably not a big deal, because I was worried that if you put a lot of noise into your supply, because I don't have the original Fluke adapter, and the original Fluke adapter is $100, which is ridiculous. So anyhow, I'm not going to pay that much money for that. So this guy will maybe, I thought, maybe inject some noise into the board, or maybe couple into the transformer, but again, I'm sure they have taken that into consideration. I don't see any other mistakes on it. One thing I did want to check was the circuitry for the backlight, because I felt like it was flickering, and sometimes if the voltage of the inverter is not high enough, you would see a flickering on that. So I can see this is the connector, and the connector goes into this particular line right here, and it crosses out. So of course it's connected to the high voltage transformer that's here. Now everything looks good. I don't think I have to check again. I have to check to see what voltage it's expecting, and to see if there is a particular problem. But there's a little bit of a flickering there that was annoying. But other than that, everything looks good. So I'm going to close it up. I'm going to fix this heatsink, close it up, see if I can dig out the schematic, and power it on again, do a few more tests, and that would be it. So if it seems like it's working, I was hoping to debug this with you guys, but there's really nothing wrong with it. So let's at least dig out the schematic and see what we can find. And there it is. I cleaned it, I put it back together, I fixed the can that was on top of this perfectly, exactly the shape it should be. Closed it up, cleaned it a little bit, and I put the battery in there. And since I don't have the back cover yet, I just taped it in place. I can't put this back on right now because the charger requires a very long connector that would go through this hole in here in order to reach the plug, but it doesn't, so I just left this off. But this works perfectly fine too, and I will put it there. And I'm going to go ahead and order the back cover from Fluke. I checked it out again. It's probably going to cost about $100, maybe $120 or so. That combined with the cost of this and the battery, we're looking at around maybe $300 to just under $320 or so, which is very good for a fully functional. I mean, I haven't tested all the functions, especially the inputs, which we're going to do afterwards, but I'm going to let it charge a little bit for now. It's connected at 17.8 volts, which is what the adapter is supposed to be, and it's taking 11.47 watts, 644 milliamps, so it is charging. In the meanwhile, I have found the schematic, so let's take a quick look at the schematic and the architecture of this meter. So here I found the service manual for the Fluke 192B, 196B, and 199, which is the next version, which is very, very nice. The 199C is a very nice unit. So I found this online just with a quick search. It's available free to download. And I'm going to show you a couple of things. I briefly looked over it. And it's very nice because it tells you everything. It's 206 pages, so it has every piece of information you can imagine. It even has a corrective maintenance section that tells you what to look for if there's a problem. So we could have used this if the meter was actually broken. Sorry that I'm filming my screen. My screen capture program is acting up. So first thing I noticed is this guy. They have documented exactly that little problem that I noticed, that I told you there was a little botch, and it's exactly what I said it is. It's a diode V4015 in series with an inductor, and they tell you exactly what to do and how to connect it and how to correct this problem if you're a technician and you're doing some corrective maintenance on it. And it tells you exactly what it is. So I was correct about the fact that it was indeed a diode in series with an inductor in there, and it's doesn't tell me exactly why they've done that, but anyhow, it must have required this modification. So it has everything, including characteristics, blah 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 blah. It tells you all possible configurations, and here's a block diagram. Let me flip it that way. So oops. So the block diagram has, I hope you probably cannot see it very well. There it is. Here's the full block diagram. So the architecture is fairly obvious. I mean, we know what to expect. Here's the input A, which is one of the RF inputs, and here's input B, which is the other at the bottom, which is the other RF input, and here is the volts ohm diode test, 2 ports in the front. And exactly as I was saying, there are transformers. Those are the big orange things, and there were optocouplers in there that connect the signals, which are completely electrically isolated from the rest of the circuit. And this is normal because you don't want any electrical connection, direct electrical connection between the inputs to the circuit and all the digital portion of the circuit afterwards. So we have here again some here the capacitors that we were seeing on each of the channels. There is an AC and a DC mode. So one of those capacitors, that relay that was in the front that we saw was this relay, the relay that selects between an AC coupled or a DC coupled oscilloscope input. And here is the C ASIC, which is the converter ASIC. So maybe this is the full ASIC, although I doubt that. I don't believe this is. I'm not sure what this C ASIC does, but it seems like it splits the high frequency, the clock and the data, and the low frequency back. Oh, you know what this might be? This might be a sample and hold or a track and hold in the front. It's probably what this is. It's a track and hold in the front and has a low frequency and a high frequency output, which then connects to the S ASIC, which I'm assuming S stands for sampling. I'm not sure. And which has a high frequency and a low frequency component. So this guy must be that big ASIC that we saw in the middle, and it receives all the signals from all the 3 channels and does all the computation in there. And there is an ADC section. There it is. This is an ADC section that follows the S ASIC, and then it follows with the D ASIC, and this must be that big ball grid array component that we saw with the green border. This must be where all the digital computation is done. You can see it interfaces with the RAM. There is some more RAM interface with the SASIC here. There is some slow ADCs here that must do some other, yeah, actually you can see it says battery temperature, battery current, battery identification, the voltage of the battery. So this slow ADC feeds back onto the digital ASIC, which then tells the unit how much battery is left and so on and on. And there is then PASIC, which I'm assuming means P is for power, and where the battery charger, the nickel metal hydride battery, and the backlight flyback converter, which is the to power on the backlight, is all controlled with this. So there is the SASIC, the DASIC, the PASIC, and 2 CASIC. So they have broken this up into multiple sections. Each of them performs a specific function. Some sampling maybe here, some digital ASIC, some power management ASIC, and some front end, maybe C is the converter. I'm not sure because it doesn't have that much data output. But anyhow, I can look in more detail on just to make sure. But the architecture is basically what we were thinking. And you can see the display is controlled by the digital ASIC, of course, because that's what all the DSP and all the display drivers are. The buttons are controlled by also feedback onto the digital ASIC. The serial interface with the optical RS-232 interface is connected there as well. Here's the backlight converter that connects to the backlight lamp, and fairly straightforward. And as we can see, the architecture is pretty straightforward. The magic, of course, happens in these ASICs, which they don't tell you what's inside them because they've been rebranded for their own use. So if I continue on the data sheet, oh, now the page is upside down. There it is. If I continue on, it has gives you a whole bunch of explanation. Actually, here it is. So this is the channel. This is the block diagram of one of the channels in a little bit more detail. This is the first time I'm looking at this, so I'm kind of thinking out loud here with you guys. This is the channel ASIC, so maybe CASIC stands for channel ASIC. There's a high frequency path, there's a lower frequency path, and there's an output stage which goes to the high frequency transformer output and the low frequency optocoupler output, which makes sense. They pass their high frequency signal through a transformer. That's how they couple the high frequency signal to the rest of the circuit, but the low frequency signal couples through an optocoupler because it has enough bandwidth. The supply and some bus control and so on are in there, so you can see some input protection, some high frequency attenuator, and so on are all built there. So it says the CASIC shows the block diagram of the CASIC. The CASIC consists of separate input paths for high frequency and low frequency signals, an output stage that drives the separate high frequency and low frequency isolation facilities, and a control block that allows software control of the modules. So it doesn't have a track and hold amplifier like I thought it does. It's probably because the conversion is only at 1 gigasample per second. To put a track and hold amplifier in the front of an oscilloscope, which then spreads out and goes into an ADC, is a common practice. And the reason for that is because you can clock your track and hold amplifier at the full sampling rate, but with multiple phases. Or, I'm sorry, you could clock it at the lower sampling rate, but with multiple phases. And that it goes into a time-interleaved analog to digital converter architecture, which then can sample the data in different phases in order to not need a full rate ADC. Anyhow, maybe I'll do a video sometime about data converters and exactly how ultra high speed data converters operating at 50, 60, 70 gigasample per second actually work, because I've built them before. So again, there's more. There's the CASIC here, the SASIC, which I'm guessing was the sampling ASIC, and so on and on. It gives you a whole bunch of other information. It gives you the diagram for the trigger and how the triggering circuit works. We can spend hours and hours on this, to basically figure out exactly how it's all the timing diagrams and so on, the operation. This tells you how to calibrate it. So actually all the calibration and testing and verification of the functionality of the unit is explained here, which is nice. If you want to calibrate the unit, you can use this if you have sufficient instrument to do so. And there is the disassembly instructions, it seems here. Yeah, it tells you how to take the pieces off and so on and on. Actually, this is what I originally saw on the Fluke website. So you can order all the bits and pieces. So I need this back cover. And that's how I found out how much it costs. It tells you how to disassemble it further, nothing fancy. This is the, okay, so this is This is actually the corrective maintenance, I believe, section. So it tells you, okay, open it up and put it on the side so you can have the cables connected. So you can see both the display and the complete circuit here, so you can do, look and see what it is. Actually tells you how the charger circuit works, how to look for problems, tells you the location of all the components, which is very nice. It's basically everything you would ever want to know about this unit is available here. There's a list of replaceable parts, and yeah, okay, there you go, there's a diagram again, some other minor things, nothing serious, and the list of all the ASICs and every component that's on there. Of course, they don't tell you what's inside the, you cannot buy that, you have to buy it directly from Fluke, the specialized ASICs. And here are the circuit diagrams. Where are this? There it is. So this is the scope channel A schematic, which we saw. Really, the block diagram is more interesting because there's a lot of detail in here that's not very interesting at all. This is channel B, whole bunch of stuff again. This is the master trigger, so you can see that the way they do actually their triggering, because it has to, the trigger is always a separate circuit in order not to have to spend DSP in order to find the trigger point. So they usually have a separate trigger circuit. This is normal for all kinds of oscilloscopes. This is the sample and trigger circuit, which uses the S ASIC, and which I believe does this. The sampling is also done here. And this is the S ASIC supply, all the supply and the decoupling caps and inductors and all the things that are required to give an analog to digital converter sampling circuit. It's a good supply with all the references. It seems like there is there's the ADC for the old and the main. So much detail about maybe that there's an old version and a new version of this. This is the schematic for the digital control. So this is that big digital ASIC that connects to the ADC, ADC-A right here, and connects to the ADC-B there, and so on. So again, I can look into more details. And this is the battery charger circuit. So here's the battery, connects here. This is the power supply that connects here, goes through the filter, and goes into the switching. The switch here, controlled by these inductors, control the charge. So the PASIC monitors the temperature of the battery, the voltage of the battery. It's just a simple nickel metal hydride battery charger. This is the flyback converter with all the transformers to reach the voltage in order to turn the backlight on. Some slow ADCs that monitor the voltage of the battery, optical interface circuitry, the TL converter, backlight converter circuitry, and this is the layout of everything. So this is all the channels. You can actually recognize it. Here's the ASIC, here's the D ASIC. As I was mentioning, this is the power ASIC, and the sampling ASIC. I'm sorry, that's the sampling ASIC right here. So the lines that come from here and go into the sampling ASIC are here. So this is where the conversion probably happens. This is the back, and some more information, so on and on. That's it. Some modifications and some other information. So you can find this online and take a look at it. But it seems to it has tons of detail in there, so you can learn exactly how this works. But by initially looking at it, it's pretty much what I was talking about. So there's nothing surprising there. You can read all about it and find out. So let's do a couple of more quick tests on this to make sure that everything works, and that will be it. So here we go. I've connected this now to two probes, like so. So we can make use of the actual meter inputs. So if I press on the meter, it starts to, actually you should be able to, let me turn the slide up, you should be able to read it when it's lying down. There you go. So if I connect them together, I should see read 0, and it does read 0, no problem. Let me zoom in a little bit more. So let me measure now the voltage that's of the power supply that's actually used to charge itself. So it should read 17.8 volts. There you go, 17.8 dead on, so it's perfectly accurate. I can try measuring some resistance, let's say. I can click on measure, and it measures ohms, continuity, diode, temperature, obviously with an external thermocouple, voltage and current. So let me measure ohms, enter. So now it says overload 50, 500, 5 meg, 30 meg. So its auto ranges all the way to the end. So let me short it, see how fast it auto ranges to 0. There you go. There you go. Pretty fast. 0.1 ohm, which is the cable, of course. seems to be perfectly fine. Let me see what else can I measure here quickly. Let's see the continuity, see how fast it reacts to continuity. Almost instant. Of course, all Flukes are really good at that, and they latch, and you know, it's almost instantaneous. Perfect. I can look at, for example, I mean the diode test, just as a last thing. I guess if I connect it, it says 0 volts because the diode, that would be like a broken diode. You know, it's perfectly fine and everything works. It can measure AC and DC current together, of course. And if I put it on this mode, I heard a click. Oh, it actually gives me a probe sensitivity, so depending on what you're using, 100 microvolts per amp, 1 millivolts per amp, and so on, all the way to 100 volts per amp for measuring very low current. So seems perfectly good. If I connect them together, no current. When it's not connected together, for some reason, oh, it's probably because of the probe, that's why it's not intended to be used in this way. But it seems perfectly fine. Everything looks good. I can do some more in detail tests later, but I don't know why it was listed as non-functional, but I can't find anything wrong with it at the moment. Well, that's about it. I was hoping to fix it and debug it, but at least it's working, so we're going to use this for fixing something else in the future. I have a bunch of broken stuff that I like to fix, so I'll make more videos about that. See you next time.